The next example relates to the extension of a linear spring. There are springs in our everyday life. The vehicles that you ride in have a spring attached to each one of the wheels. So let us understand how we can analyze a spring. A spring is represented in the following form. Let us assume that we have a spring that is attached rigidly and firmly somewhere. Here is our spring. And when we have a spring, we need to provide a parameter called spring constant, K. Now, if I apply a force on this spring, and this force will be a force that will try to increase the length of the spring, then this spring will increase in length by a certain amount, that is a function of the spring constant. So this is the increase in length, let's say x. So now we observe that we have three parameters, f, k, and x. The relationship between these three parameters is the following. The force is equal to the spring constant times the elongation x. From here, we can also solve for x. If we divide both sides by x, we find f over x equals to k, or we can find out x being f over k. Here, if we look at the first equation, we recognize that if x is the independent parameter, k is the slope, and f is the independent parameter. If we look at the last equation, we can recognize that f is the independent parameter, that's the amount of force that we put. 1 over k, not just k, but 1 over k is the slope, and x is the dependent parameter, is the amount of elongation. So these are forms of linear equations. So let me write here m equals 1 over k, and here m equals k. So this shows to us how the slope changes depending on whether the force is the dependent parameter or whether the distance is the dependent parameter or the extension of the spring. If we were to analyze a spring and put some numbers into these expressions, let us say that we have a spring with a spring constant of 100 newtons per meter. So the spring constant has units of force per distance. We apply a force of 2 newtons, and we are interested to find how much this particular spring will change in length. Well, in order to solve for this, we need to use the last equation. X equals 1 over k times f, or 1 over 100 newtons per meter times F. So this shows us now the equation of a line where the constant is 0. So if we were to plot it, we will have here the independent parameter, which is the force. On the vertical, the dependent parameter, which is the distance. And this plot or this line will be going through the origin with a slope of 1 over 100 newtons per meter. So you observe that there is a linear relationship. And when you're working with springs, please keep in mind that this linear relationship is true only up to a certain extension of the spring. It's not true for an unlimited extension because the material undergoes certain deformations from the elastic to the plastic regime. And if you exceed the elastic limit, it will not be able to recover and it will be permanently deflected. And of course here you can substitute 2 newtons for F and find out the elongation. And this plot here shows to us that there is a linear relationship. So if the force now is doubled from 2 to 4 newtons, the displacement or the elongation will increase by 2. If the force becomes 20 newtons, which is a multiplication by 10, then the elongation will change or increase by 10 times. And I will let you find the actual numeric value for this example.